A probe weighing only a few grams and a ship carrying thousands of people could both be sent toward the same star. Yet comparing them by top speed would tell us almost nothing about which one had the better engine. The tiny probe begins with an enormous advantage. It needs no living space, no food, and almost no protection. It can endure acceleration that would injure a human crew, and when it reaches the destination, it may simply race through the system without slowing down. A crewed ship has to do something much harder. It must protect its passengers throughout the crossing, keep its machinery working for decades or even centuries, and arrive slowly enough to remain near the world it came to reach. So the fastest craft would not necessarily be the most capable one. Proxima Centauri, the closest star beyond our Sun, lies a little more than 4 light-years away. Voyager 1 is leaving the solar system at about 17 kilometers per second, or 38,000 miles per hour. At that speed, traveling as far as Proxima Centauri would take roughly 75,000 years. Voyager is not heading there, but the comparison shows what interstellar distance does to a speed that already feels extraordinary. Against the gap between stars, it becomes almost negligible. More advanced engines could shorten that journey enormously, although every improvement changes something else about the ship. A powerful engine may need more fuel. More power creates more heat. Greater speed makes collisions with gas and dust more destructive, and whatever accelerates the ship must eventually help it slow down again. That means there cannot be one winner for every mission. A laser-driven sail may be the best way to send a tiny probe past another star. Nuclear propulsion may become more attractive when the payload grows heavier. Fusion could offer the strongest path for a large inhabited vessel, but only if the reactor, fuel system, and cooling equipment can survive far longer than anything we have built. Even antimatter, which releases more energy from its mass than any conventional fuel, does not escape the comparison. Producing it is difficult. Storing it is harder. Turning that energy into controlled thrust without destroying the ship may be harder still. And beyond those ideas sits warp travel, which can be described mathematically, but cannot yet be treated as an engine that engineers know how to build, weigh, or test. So the real question is not simply which starship could move fastest. It is which propulsion system could carry a useful payload across interstellar space, survive the consequences of its own speed, and arrive in a condition that still allows the mission to succeed. By the end of this video, you will understand which engines are strongest for journeys within our solar system, which might send the first probes to another star, and why the best option for a human generation ship may be completely different from the fastest design on paper. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. Calling something the fastest starship sounds simple until you ask what the ship has to carry. A tiny probe can cross a finish line that a crewed vessel could never approach. Give both designs the same medal, and the contest stops telling us much. So we need several races. The first is a probe flyby. It only has to reach another star and pass through the system. It may be extremely small. It doesn't need fuel for braking, rooms for people, or supplies for a return. That makes it the lightest race, though far from an easy one. Then there's the captured probe. This machine has to slow down after the crossing. Reaching the star at great speed is no longer enough. It must arrive with some way to brake, enter orbit, and spend time near its targets. That extra task can add a great deal of mass before the probe even leaves home. A crewed ship faces a different contest. People need air, water, food, living space, medical care, and protection from radiation. The ship must keep its passengers alive while its engines run, while it coasts, and while it slows down. A design that delivers a camera may be hopeless at delivering a person. And then we have a generation ship. Its passengers may live and die aboard it, with their descendants completing the trip. Speed still counts, but reliability takes on a different meaning. The vessel has to function less like a vehicle and more like a small, closed world. Even within one race, top speed is only one line on the scorecard. Acceleration counts too. A probe might survive a violent burst that would injure a crew. A gentler ship may take years just to reach cruising speed. Travel time depends on that acceleration, the cruise speed, and the time needed to brake. Then shielding adds more weight. At high speed, even thin gas and tiny dust grains can strike with enormous energy. The faster the ship goes, the harder its front surface has to work. Heat has to leave somehow. Engines, reactors, electronics, and people all produce it. In space, you can't cool a ship by opening a window or blowing air across the hull. The heat must be sent away as radiation, usually through large radiators. Onboard power counts separately from thrust. Instruments need electricity during the crossing. So do computers, life support systems, communications, and cooling equipment. A powerful engine is of little value if the rest of the ship goes dark halfway there. We also have to ask whether the technology is ready. Some designs use hardware we already understand. Others depend on materials, reactors, or fuel systems that haven't been built. And every ship needs support on the ground or in orbit. Launch systems, power stations, fuel factories, construction yards, and perhaps machines spread across the solar system. So there is no single fastest design. There are winners for particular payloads, missions, and levels of risk. Once we separate those races, we can finally compare the engines fairly. Which kind of traveler are we trying to send? Most engine comparisons begin with the number everyone wants to see, top speed. It feels decisive, like checking which car has the highest figure on the speedometer. But an interstellar ship isn't doing a lap. It has to carry something worth sending, survive the trip, slow down, and arrive in working order. So the first column on our scorecard is Payload class. A probe the size of a coin asks very little from its engine. A robotic laboratory asks much more. A crewed ship adds food, water, living space, spare parts, and years of protection. An engine that wins with a tiny probe may fail completely when the payload grows. Then comes acceleration. High speed means less if reaching it takes most of the voyage. Some engines push hard for minutes. Others provide a faint shove for years. That slow pressure can build enormous speed, but only if the ship has time and power to keep the engine running. Cruise speed belongs on the page, of course. So does total travel time. They aren't the same number. A ship may spend years accelerating, coast briefly, then spend years braking. If a proposal quotes only its fastest moment, it can hide most of the trip. Braking is where several exciting designs become awkward. Reaching another star at a large fraction of light speed is only half an arrival. Without a way to slow down, the ship flashes through the target system and keeps going. That may suit a camera taking hurried measurements. It doesn't suit a lander, an orbiter, or anyone hoping to stay. Shielding also grows harder as speed rises. Space contains thin gas and tiny grains of dust. At ordinary spacecraft speeds, those particles can damage surfaces. At interstellar speeds, each impact carries far more energy. The shield adds mass. More mass demands more thrust, more fuel, or more time. Heat brings another penalty. Engines waste energy, electronics make heat, and shields absorb impacts and radiation. On Earth, warm machinery can pass heat into surrounding air or water. A spacecraft mostly has to radiate it away. That requires large surfaces, careful temperatures, and still more mass. Onboard power gets its own column. The engine may need electricity, but so do guidance, communications, computers, cooling pumps, and scientific instruments. A drive that works only beside a vast external power source faces a different contest from one that carries its energy supply. Then we grade readiness. Has the engine fired in a laboratory? Have its materials survived the required temperature? Can its fuel be stored for decades? A design backed by tested parts should not receive the same confidence as one that depends on a reactor or sail material no one can yet manufacture. Finally, there's the burden outside the ship. Some plans need one launcher and a ground station. Others need lasers spread over kilometers, fuel made near the sun, or construction yards in orbit. The engine may be compact, while the machine that launches it is larger than a city. Put all those columns together, and the easy winner disappears. Speed still counts, it just has company. The next comparison begins by choosing what must arrive, because the traveller changes the race before any engine starts. Chemical rockets look disappointing only when we ask them to cross the space between stars. Around Earth, they're astonishing machines. A Saturn V could lift more than 6 million pounds at launch, which is about 2.8 million kilograms, and send people toward the Moon. Modern rockets routinely place satellites in orbit, dispatch probes toward other planets, and adjust their paths with remarkable precision. The basic action is familiar. Let go of an inflated balloon, and air shoots one way while the balloon moves the other. A rocket does the controlled version. Fuel and an oxidizer react inside a chamber. The hot gas rushes through a nozzle at high speed, pushing the vehicle forward. It works even in a vacuum. A rocket doesn't need air to push against. It carries what the chemical reaction needs, and it gains momentum by throwing exhaust backward. The problem is how much energy chemistry can release from each pound of propellant, and how much propellant must be carried to accelerate the rest. This creates an awkward pattern. Add fuel and the rocket can change its speed more. But the new fuel has mass, so still more fuel is needed to accelerate it. Then tanks and engines must grow to hold and burn that fuel. Staging helps by dropping empty hardware, but it doesn't remove the underlying limit. Voyager 1 gives us a sense of the scale. It's leaving the Sun at roughly 38,000 miles per hour, or 17 kilometers per second. That's fast enough to cross the continental United States in less than 6 minutes. Yet Proxima Centauri lies about 25 trillion miles away, or 40 trillion kilometers. At Voyager's present speed, the trip would take roughly 75,000 years. Voyager was never designed for that trip, of course. Its speed came from its launch, and gravity assists around Jupiter and Saturn. Still, the comparison shows the size of the gap. Chemical propulsion can make a superb planetary probe while remaining far too slow for a human timescale between stars. A nuclear thermal rocket changes the furnace, not the basic bargain. Instead of burning fuel with an oxidizer, a reactor heats a light propellant, usually hydrogen, and sends it through a nozzle. Because the exhaust can leave faster, the engine can produce about twice the specific impulse of a typical chemical rocket. NASA and the Atomic Energy Commission tested nuclear rocket engines during the Rover and Nerva programs in the 1950s and 1960s. They ran reactors on the ground and showed that the core idea worked. Such engines could shorten some crude trips within the solar system and reduce the propellant burden. Twice the exhaust performance is valuable nearby. Across 25 trillion miles, it's still a local improvement. The distance to Proxima doesn't merely ask for a better rocket. It exposes how little chemical energy, or even a hot reactor, changes the scale of the crossing. Chemical rockets are very good at one violent job. They burn fuel, throw hot gas backward, and push a spacecraft forward. Every launch you've ever watched depends on that exchange. The trouble is that a chemical engine carries both its fuel and the material needed to burn it. Most of the vehicle at liftoff is propellant. Burn some, become lighter, then burn more to speed up the smaller vehicle that remains. This is why rockets grow into tall stacks. Much of the rocket exists to lift the rest of the rocket. For missions around Earth, the Moon, and nearby planets, that bargain can work. Apollo crossed to the Moon in about 3 days. Robotic missions reach Mars in months. These are difficult trips, but chemical propulsion can place them within a human lifetime. Proxima Centauri changes the arithmetic. It sits about 25 trillion miles away, roughly 40 trillion kilometers. Even a spacecraft moving at 36,000 miles per hour, or about 58,000 kilometers per hour, would need nearly 80,000 years to arrive. That speed is already far beyond any car, aircraft, or bullet. Against interstellar distance, it barely registers. Nuclear thermal propulsion gets more motion from each pound of propellant. Instead of burning hydrogen with another chemical, a reactor heats the hydrogen directly. The gas becomes extremely hot, It expands and races through a nozzle. Because that exhaust leaves faster, the engine can produce about twice the specific impulse of a typical chemical rocket. That's a real improvement. The spacecraft needs less propellant for the same change in speed. It could carry more cargo, accept more shielding, or finish certain trips through the solar system sooner. For a crew heading toward Mars, those savings could reduce radiation exposure and the food they must carry. They could also mean less time inside a cramped vehicle. Months count when people are aboard. NASA and the Atomic Energy Commission tested this idea during the rover and Nerva programs in the 1950s and 1960s. Reactors ran on the ground, heating hydrogen and proving that the basic engine worked. This isn't a machine invented only on paper. Yet twice the exhaust performance doesn't mean twice the practical interstellar speed. The spacecraft must still carry propellant. Tanks have mass. So do the reactor, radiators, shielding, structure and equipment that keeps hydrogen cold. Every added part must be accelerated with everything else. Speed also becomes more expensive as you ask for more of it. More speed requires more propellant. Then some propellant is spent accelerating the added propellant. The demand rises sharply, while the engine's advantage stays limited. So nuclear thermal propulsion deserves serious attention. It may change what crews can do around the Sun, but it doesn't turn Proxima Centauri into a practical destination. It improves the engine while leaving the scale of the crossing almost untouched. That leaves an awkward choice. We can carry our energy and propellant with us, accepting their mass, or find a way for the spacecraft to receive its push from somewhere else. Ion propulsion seems like the obvious escape from that awkward choice. It uses propellant so sparingly that a spacecraft can keep changing its speed long after a chemical engine would have emptied its tanks. There's real beauty in that. The engine takes a small amount of gas, strips electrons from its atoms, and throws the charged particles backward at tremendous speed. It's a little like moving a heavy table by flicking grains of rice at it. Each grain does almost nothing. Keep the stream going though, and the nudges add up. An ion engine works through that same patient accumulation. Its exhaust leaves far faster than the exhaust from most chemical rockets, so each kilogram of propellant provides much more change in motion. We already use this approach. NASA's Dawn spacecraft entered orbit around Vesta, left it, and later entered orbit around Ceres. That would have demanded far more propellant with ordinary engines. Dawn's ion thrusters burned for years in total, slowly reshaping the spacecraft's path while using only a modest supply of xenon. But slowly is the important word. Ion engines save propellant because they push a small amount of it to very high speed. They don't push much at once. A chemical rocket can press you firmly into your seat. A typical ion thruster would struggle to hold up a sheet of paper against Earth's gravity. In open space, that faint pressure can build speed for months or years. For robotic missions, that may be an excellent trade. The spacecraft doesn't get tired, it doesn't need food, and it doesn't mind taking the scenic route. A crew does. Every extra month means more supplies, more radiation exposure, more equipment wear, and more chances for something small to become serious. Time becomes part of the vehicle's mass, because keeping people alive requires hardware and supplies. The electricity also has to come from somewhere. Near the Sun, large solar arrays can feed electric thrusters. Farther out, sunlight weakens, and the arrays become less helpful. A nuclear electric spacecraft could carry a reactor instead. The reactor would produce heat, turn some of that heat into electricity, and power the engines for a very long burn. That sounds compact until you include the whole machine. The reactor needs shielding and power conversion equipment. Most of its heat cannot become electricity, so broad radiators must release the leftovers into space. Those radiators have mass, so do their pumps, pipes, supports and protection. Raising the electrical power usually makes this cooling problem larger. None of this makes electric propulsion a disappointment. It's extraordinarily efficient, and nuclear electric power may send heavy robotic craft across the solar system with far less propellant. Yet efficiency alone doesn't give a crew a short trip. These engines trade a violent, brief burn for a gentle push sustained across years. They reduce the propellant bill, while time, reactor mass, and radiator mass take its place. Electric engines can make a spacecraft's exhaust race away at astonishing speed. That sounds like the answer to the propellant problem. Each bit of propellant does more work, so the ship can carry less of it. But an efficient exhaust plume doesn't mean a powerful shove. It's closer to pushing a shopping cart with one finger. You waste very little effort, and the cart does move. You just need patience. In space, that finger may keep pushing for months or years. Iron engines have already shown how well this can work. NASA's Dawn spacecraft used electric propulsion to visit Vesta and Ceres. Its engines could change the craft's speed by a large amount, while using little propellant. At any one moment, though, the thrust was about as forceful as a sheet of paper resting on your hand. Dawn gained speed because that tiny force continued day after day. For a robot, that can be a fine bargain. A machine doesn't get bored, lose bone, or need fresh food while the engine slowly builds speed. A crew changes the calculation. Every added month means more supplies, more protection, more equipment, and more chances for something important to fail. Saving propellant can therefore make another part of the spacecraft heavier. More electrical power can produce more thrust, so a nuclear electric spacecraft might carry a reactor instead of depending on sunlight. The reactor makes electricity, and the electricity drives the engines. On paper, the arrangement looks wonderfully economical. The paper leaves out the cooling system. A reactor turns only part of its heat into electricity. The rest has to go somewhere. On Earth, a power plant can pass waste heat into air or water. Space offers neither. The spacecraft must radiate that heat away as infrared light, using large panels that stay exposed to open space. Those panels aren't weightless. They need pipes, pumps, frames, working fluid, and protection from tiny impacts. The reactor needs its own structure and shielding. Power converters and cables add more, increase the reactor's output, and the spacecraft often needs still more radiator area to shed the extra heat. Even a very efficient engine can inherit a surprisingly bulky power plant. So the mass hasn't vanished. It has changed jobs. Less propellant may be needed, but the ship now carries a reactor and its cooling hardware. If designers trim the reactor, thrust falls and the trip grows longer. If they demand more thrust, the machinery grows heavier. No single design escapes all four costs at once: propellant, thrust, travel time, and power system mass. Nuclear electric propulsion may be excellent for cargo, probes, and missions that can wait. It can keep applying a small push until that push adds up to a remarkable change in speed. For people crossing enormous distances, though, low thrust turns efficiency into a long stay aboard the ship. Perhaps the engine doesn't need to carry its source of power at all. A sail begins with that different bargain. Let sunlight or a distant beam provide the push from outside. A sail looks like the cleanest escape in the room. No fuel tanks empty as the ship accelerates. No exhaust has to be thrown backward. The source of the push can remain millions of miles away, while the spacecraft carries little more than a broad reflective sheet. After all the penalties imposed by onboard propellant, that arrangement feels almost suspiciously elegant. The push comes from light itself. A photon has no rest mass, but it does carry momentum. When sunlight strikes a sail and bounces away, a tiny amount of that momentum passes to the sail. One photon does almost nothing. A steady flood of them can produce a continuous force without consuming any material aboard the ship. You've seen the gentler version at home. Sunlight falls across a curtain and warms it, even though the beam feels weightless. A sail asks that beam to do more than deliver heat. It asks the light to press on a surface and move the whole craft. And light really does press. In 2010, Japan's Icarus spacecraft opened a solar sail about 20 meters across, roughly 66 feet. Instruments aboard the craft measured the slight acceleration caused by sunlight. 5 years later, the Planetary Society's Light Sail 2 mission used a sail about 32 square meters in area, around 344 square feet, to alter its orbit around Earth using sunlight alone. So the principle is settled. The difficulty hides in the scale. At Earth's distance from the Sun, light pressure is extremely weak. It gives a perfect reflecting surface only a few millionths of a Newton for each square meter. A large sail may catch plenty of sunlight and still receive less force than the weight of a small coin in your hand. That's why sail area by itself tells you very little. The better number compares the area catching light with all the mass that light must move. A wide sail attached to a tiny probe can gain speed steadily. Attach the same sail to a crew cabin, shielding, food, radiators, instruments and structural supports, and the acceleration drops. Making the sail larger sounds like the easy answer, but every extra square meter adds film, cables, supports, and deployment hardware. Those parts add mass. They must also survive launch while folded, then open without tearing, wrinkling badly, or tangling. A sail large enough for a human vessel could span an enormous distance while remaining thinner than materials we normally trust with anything important. A powerful laser beam could press much harder than sunlight. It could also keep pushing after the craft had travelled far from the sun. Yet the same ratio remains in charge. The beam supplies force across an area. The sail and payload supply mass. More beam power helps, but it brings its own demands for aiming, cooling, and keeping light centered on a receding target. The graceful idea, then, rests on an unforgiving fraction. How much light the sail catches compared with how much spacecraft it must carry. Seen from far away, it's a bright sheet crossing the dark without fuel. Seen by an engineer, it's mostly area trying to outrun mass. Sunlight feels warm on your face, but it barely pushes you. Each packet of light carries momentum. When it strikes a surface, it gives some of that momentum away. A reflective sail gets a little more because the light bounces back. Spread a thin mirror across enough space, and those tiny nudges add up. Near Earth, direct sunlight produces only a few millionths of a Newton per square meter. That's roughly the weight of a small paperclip spread across a large room. It doesn't sound promising. Still, the pressure arrives every second without using stored fuel. Given enough time, a very light sail can build real speed. In 2010, Japan's Icarus spacecraft opened a sail about 14 meters across. That's around 46 feet. Sunlight changed its motion as planned. The Planetary Society's light sail too did something similar in Earth orbit in 2019. It raised one side of its orbit using sunlight alone. These missions proved the push is real and controllable. But proof of motion isn't proof of a practical transport system. A soap bubble moves easily when you blow across it. Tape a phone to the bubble, and the experiment ends rather quickly. A sail faces the same problem. Every support cable, instrument, antenna, computer, and protective layer adds mass. The light doesn't become stronger merely because the cargo is important. Sail designers compare the total mass with the sail's area. A wide sail with very little attached mass can accelerate well. Add a heavy payload without making the sail larger, and acceleration falls. Make the sail larger, and its own structure grows heavier. It must unfold without tearing, stay flat enough to steer, and survive heat and tiny impacts. There's no free square meter. This ratio also decides how long the mission must wait. Half the acceleration, and the craft needs much longer to reach the same speed. That may be acceptable for a small experiment. It becomes harder when instruments age, electronics face radiation, and mission teams must keep listening for years. Time carries weight of its own. Distance makes the bargain worse. Sunlight spreads as it leaves the sun. At twice Earth's distance, a sail receives 1/4 of the light pressure. At 5 times the distance, near Jupiter, it receives about 1/25. The sail may still be moving fast from earlier acceleration, but its ability to gain more speed fades just when the voyage is becoming long. That creates an awkward split between demonstrations and missions people usually care about. A small sail carrying a tiny sensor can wait patiently for speed. A probe with serious instruments needs more structure, more power, and more ways to communicate. A crewed craft would need shielding, life support, supplies, and somewhere for the crew to live. The sail hasn't changed, the burden behind it has. So sunlight can remove the propellant tank without removing the arithmetic. The mission still has to match a weak push, a shrinking supply of light, and a payload that refuses to weigh nothing. For very light craft, that trade can be excellent. For larger ones, gentle pressure and long patience are only half the system. The missing half is a way to supply much more light. A laser changes the scale of the push because it doesn't have to wait for sunlight. Breakthrough Starshot takes that idea seriously. Its proposed craft would be tiny sensor packages attached to sails only a few meters wide, driven by a vast laser array on Earth. The target is Alpha Centauri, a little over 4 light-years away. The plan calls for sending these little probes to about 20% of light speed. That's roughly 134 million miles per hour, or 216 million kilometers per hour. At that speed, the crossing could take about 20 years instead of tens of thousands. Those numbers sound like science fiction. The underlying physics does not. In 2016, physicist Stephen Hawking and investor Yuri Milner announced the Starshot program with a research effort meant to test the difficult parts. Researchers have since studied sail materials, laser control, atmospheric distortion, and whether a fragile craft could survive the trip. The sail would face an extraordinary beam. It must reflect nearly all the incoming light, because even a small amount of absorbed energy could burn it. It must stay centered while the beam pushes from millions of miles away. The laser array would also need to act as one enormous instrument, keeping many separate beams in step through moving air. Even if all of that works, the probe arrives with a problem. It's moving far too fast to stop. Alpha Centauri has no matching laser array waiting at the other end. The craft would cross the system in a matter of hours, taking whatever measurements it could before continuing into interstellar space. Then those measurements must reach Earth. A probe light enough for this trip cannot carry a large dish or a powerful generator. Its message would be faint, sent across more than 4 light-years, and it would take another 4 years to arrive. The flight may last 20 years. The first signal with scientific value could come closer to 25 years after launch. And this is where the scoreboard needs a careful label. A successful Starshot-class mission would be an immense win for engineering. It could become humanity's first close look at another star system. But it would be a fast flyby by an ultralight probe, not a general method for moving large spacecraft between stars. That difference is easy to miss when one spectacular speed becomes the measure of the whole mission. Add better cameras, shielding, power storage, steering, or a braking system, and the mass rises. More mass demands more laser energy, a larger sail, or a lower speed. None of those changes is free. A machine that weighs a few grams can accept hardships that a scientific observatory cannot. So laser-driven sails may give us our first interstellar visitor. They do it by making the traveler extremely small, the launch system extremely large, and the arrival extremely brief. A probe racing through Alpha Centauri at 1/5 the speed of light would cross the whole system in a few days. The nearest planet might stay close enough for detailed study for only a few hours. Then the probe would be gone, carrying its instruments into empty space with no road back. That can still be a remarkable mission. A tiny camera could take images from a place no human machine has visited. Other instruments might sample dust, magnetic fields, and charged particles. Several probes could arrive along different paths. If some failed, others might survive. Starshot-class proposals take this possibility seriously, and the physics behind the basic claim is serious too. But reaching another star and stopping there are very different achievements. It's like driving past a house at highway speed and trying to inspect the rooms through one open window. You may collect something valuable. You haven't arrived in the everyday sense. For a probe, slowing down means getting rid of almost all the motion that took so much energy to create. There's no enormous laser waiting beside Alpha Centauri. The probe could carry fuel, but fuel adds mass. Then it needs more energy at launch, which may require a bigger sail or a lower final speed. A larger scientific payload makes the same problem worse. Cameras need lenses, transmitters need power, electronics need protection. Every improvement arrives with weight attached. Some proposed braking methods avoid carrying all the required fuel. A sail might turn toward the light of the destination stars and use their photons to slow down. A magnetic sail might push against the thin stream of charged particles between the stars. These ideas obey known physics, but they impose harsh limits on speed, sail size, material strength, and navigation. They may also stretch the trip by decades. The target system won't make the maneuver easy. Alpha Centauri contains 2 bright stars moving around each other, with the smaller red star Proxima much farther away. A probe trying to break with starlight must approach on a very precise path, miss the planned angle, arrive with the wrong sail shape, or lose control during the pass, and there may be no second attempt. Even communication becomes awkward. A gram-scale probe must send data across more than 4 light-years with very little onboard power. A larger antenna would help. So would a larger power supply. Once again, the cure makes the traveler heavier. This doesn't make a fast flyby meaningless. It defines the win more clearly. We might send something astonishingly small through another star system and receive a thin stream of measurements years later. That would be an interstellar mission. It would not yet be an interstellar observatory that slows down, studies a world through its seasons, changes course, and remains on duty. Arrival isn't the final detail added after speed. Arrival is a second mission, carrying its own mass, energy, risk, and time. A beam-driven sail can win a race that almost nothing else can enter. But the winner is a probe weighing only a few grams, carrying instruments that must survive a violent launch and decades of travel. Breakthrough Starshot was built around that narrow target. Its studies described tiny spacecraft pushed by a vast array of lasers on Earth. The beam would deliver tremendous power for only a few minutes. During that brief push, the sail could reach a large fraction of light speed. The physics is serious. So is the engineering work behind it. The trouble begins when you ask the probe to carry more. A phone seems almost weightless in your hand, yet beside a gram-scale spacecraft, it's enormous. Add stronger communications, radiation shielding, a larger computer, or a better telescope, and the mass rises quickly. The sail must grow with it. Then the laser system must place more energy on that sail without burning it, tearing it, or letting the beam wander off target. That last part is easy to underestimate. A flashlight spreads across a wall as you step backward. A laser spreads far less, but it still spreads. Keeping a powerful beam focused on a small racing sail demands an array spread across a very large site. Its many beams must act like one instrument. The atmosphere bends the light. Weather interrupts it. Tiny timing errors push the sail in the wrong direction. Even if every part works, a heavier craft asks for more power or more time under the beam. More time means tracking it farther from Earth. More power means larger equipment, more heat, and a much higher cost on the ground. The spacecraft may be small, but its engine is an enormous machine that stays home. Then comes the missing brake. The launch beam pushes from behind. At the destination, that same beam is more than 4 light-years away and pointed the wrong way for stopping. The probe could carry a braking system, but fuel and engines add mass. It might use the target star's light or magnetic environment, though those methods demand extra sail area, precise navigation, and long braking distances. None has yet turned a fast gram-scale concept into practical human transport. People make the scaling mistake because a sail has no fuel tank. It feels as if removing fuel removes the main limit. It doesn't. The burden moves into the sail, the payload, the beam, and the equipment needed to slow down. So the real achievement remains remarkable, just smaller than the dream often attached to it. A Starshot-class system could give us our first close measurements from another star system. It could prove that human hardware can cross the distance within a lifetime, but it would send a speck on a flyby, not people, and not a ship that arrives ready to stay. Most engines punish you for adding mass, But nuclear pulse propulsion has an odd preference for very large ships. The machinery is so forceful and so heavy that shrinking it can make the whole design less practical. The basic idea is almost rude in its simplicity. A ship drops a small nuclear explosive behind itself. The device goes off. Hot gas and debris strike a broad metal plate at the rear, called the pusher plate. That plate shoves the ship forward. Then another device drops. Another pulse follows. The ship climbs on a controlled series of explosions. You wouldn't bolt your chair directly to that plate. The ride would be brief and medically memorable. Between the plate and the inhabited ship, huge shock absorbers spread each violent kick into a longer, gentler push. It's less like being struck by a hammer, and more like riding in a car whose suspension is doing heroic work on a terrible road. In the late 1950s, researchers at General Atomics studied this under Project Orion. Physicist Freeman Dyson was among them. The group tested small models with chemical explosives and produced serious engineering studies for nuclear versions. Their work never became a flight program, but it wasn't merely a sketch on a napkin. Engineers examined pulse units, plate erosion, shock systems, steering, and the awkward business of setting off nuclear devices near your own spacecraft without destroying it. That awkwardness never really leaves. A pulse ship needs a strong plate, massive shock absorbers, protective structure, and a large supply of explosive units. Those parts create a steep entry fee in mass. On a small vehicle, they can swallow most of what the vehicle can carry. You end up building an astonishing engine to move its own hardware. Make the ship larger, though, and the balance begins to change. The pusher system doesn't have to grow as quickly as the payload it can serve. More of the total mass can become shielding, living space, supplies, scientific equipment, or cargo. A large ship also has room for backup systems and repairs. That counts for more on a long voyage where no rescue crew is coming. With repeated nuclear blasts happening just behind you, spare parts stop sounding fussy. This doesn't mean mass becomes free. Every extra ton still demands momentum. Nor does it remove the immense problems of nuclear safety, treaties, launch operations, fallout, and public consent. You would almost certainly want to assemble such a ship away from Earth, which creates another giant project before the first pulse. Nobody has flown a nuclear pulse spacecraft, so its best performance remains calculated rather than demonstrated. Still, its scaling logic is unusual. Chemical rockets become increasingly burdened as the mission grows. Beamed sails favor payloads that are almost absurdly small. Nuclear pulse propulsion enters carrying tons of machinery before the cargo even arrives. And then the ship grows large enough that the apparent flaw becomes its reason for being. That reversal is why nuclear pulse propulsion refuses to disappear from serious studies. Most propulsion systems look best when the spacecraft is light. This one starts to look less unreasonable when the spacecraft is already enormous. The basic idea is blunt. A ship releases a nuclear explosive behind itself. The blast strikes a thick plate at the rear. Shock absorbers spread that violent shove over a longer time, so the crew and cargo feel a strong push instead of one fatal blow. Then another device is released. Another blast follows. The ship climbs through a chain of controlled explosions. Even the description sounds like something engineers should have rejected during lunch. Yet, in the late 1950s, Project Orion brought physicists and aerospace engineers together to study it. They tested small models with chemical explosives. The models did rise under repeated pulses. No nuclear version was built, but the mechanical principle wasn't fantasy. Its advantage appears in the mass budget. The plate, the shock system, the magazines, and the shielding are terribly heavy. On a small craft, they consume nearly everything you hoped to carry. On a ship weighing thousands of tons, that same machinery can become a smaller share of the whole. You can add thick radiation shielding, large living spaces, repair shops, food stores, and equipment that lasts for decades. The method doesn't become elegant, it becomes less wasteful as the mission grows. And that is precisely where the attraction runs into disgust. A nuclear pulse ship would require hundreds or thousands of explosive devices. Each one would need to be built, secured, transported, and kept reliable. A failed pulse could damage the plate. A mistimed pulse could threaten the entire ship. An accident during assembly could scatter radioactive material before the mission began. Using the system near Earth would be worse. Atmospheric blasts could produce fallout. Explosions in space could disrupt satellites and create electromagnetic effects. Even if engineers reduced those risks, nations would still have to distinguish a propulsion stockpile from an arsenal. That's not a minor paperwork problem. It touches the machinery of nuclear war. Treaties followed the same concern. In 1963, the Partial Test Ban Treaty prohibited nuclear explosions in the atmosphere, underwater, and in outer space. The agreement was meant to limit contamination and slow an arms race. It also closed the most direct path to testing an Orion-style ship. So the barrier isn't that everyone overlooked a wonderful engine. People saw the engineering promise and the political cost at the same time. A civilization capable of building the ship would also need to trust itself with a moving warehouse of nuclear explosives. That leaves pulse propulsion in an awkward place. It may be one of the few proposed systems that still has something to offer when the spacecraft becomes the size of a small town, but the scale that makes it physically attractive also makes its failures, weapons risks, and environmental consequences far harder to accept. A probe can survive by being small. A habitat can't. Once people must live inside the ship, mass arrives from every direction. You need radiation shielding, water, food, spare parts, air systems, repair equipment, and rooms where people can remain sane. Then you need extra systems in case the first systems fail. The payload stops looking like luggage and starts looking like a settlement. Most propulsion ideas punish that growth severely. Add more ship and you need more propellant. Add more propellant and you need a larger structure to hold it. That structure adds still more mass. It's like packing for a long trip, then discovering every suitcase requires another suitcase underneath it. Nuclear pulse propulsion behaves differently. The ship carries a series of small nuclear explosive units and releases them behind a huge metal plate. Each blast throws hot material against the plate. Shock absorbers spread the kick into a steadier push that the ship and its passengers could withstand. This sounds like an engine designed by someone who had run out of reasonable suggestions. Yet its strange method gives it an advantage. Nuclear explosives contain an immense amount of energy in a compact package. They don't need a combustion chamber able to hold the full event. The blast happens outside, where there's room for the material to expand. Size can even help. A larger pusher plate catches more of the expanding material. A heavier ship also responds less violently to each pulse. The machinery, shielding, and shock absorbers are still daunting, but they don't become pointless merely because the payload has grown from a probe into a town. That was part of what Project Orion researchers found during studies begun in the late 1950s. Engineers at General Atomics explored designs ranging from relatively modest spacecraft to ships weighing thousands, and in some studies millions of tons. The largest proposals were never close to construction, and their assumptions varied. Still, the calculations revealed something unusual. Pulse propulsion did not lose its appeal at the very scale where many other proposals began to collapse under their own fuel demands. There's a human consequence hiding inside that engineering result. A generation ship isn't carrying a sample of civilization. It's carrying enough civilization to repair itself after the original builders are gone. Workshops, farms, medical rooms, replacement machinery, and thick protective walls aren't optional comforts. They're the payload. Every added safeguard becomes something else the engine must move. Pulse propulsion doesn't make that payload easy to move. It doesn't solve guidance, reliability, blast debris, radiation, or the storage of thousands of nuclear units. It certainly doesn't remove the political danger. But if the requirement changes from sending a clever instrument to sending a durable human world, this old and troubling design moves upward on the list. Its case becomes stronger only when the ship becomes almost absurdly large. Fusion can seem like the more mature answer because it starts with fuel rather than a sequence of bombs. In a fusion reaction, light atomic nuclei join and release energy. The sun does this under crushing pressure. A spacecraft would have to do it inside a machine, under control, while turning some of that energy into thrust. The promise is hard to ignore. Fusion fuel can hold far more energy for its mass than chemical propellant. A fusion engine could throw exhaust backward at tremendous speed. Faster exhaust means the ship needs less propellant to gain the same change in speed. For a large interstellar craft, that's exactly the bargain you want. More ship, with less fuel carried merely to push other fuel. Several designs have tried to make that bargain real. In the 1970s, the British Interplanetary Society developed Project Daedalus, an uncrewed probe driven by tiny fusion pellets. Electron beams would ignite them one after another. Each burst would press against a magnetic field instead of a solid chamber wall. Daedalus never became hardware, but it showed that fusion could be studied as a complete engine system with tanks, timing, structure, and a destination. The trouble is that fusion doesn't arrive as a compact miracle in the engine room. You need fuel that can actually be ignited. You need equipment that can create extreme temperatures or compression. You need magnetic fields, lasers, or particle beams firing with extraordinary precision. Then the process must repeat reliably, perhaps millions of times, without shaking the ship apart. And the released energy doesn't politely become thrust. Some becomes heat. Some may arrive as high-energy neutrons that pass through machinery and damage materials. Shielding adds mass. Damaged parts need replacement. Heat must reach vast radiators, because space offers no breeze or ocean to carry it away. A radiator large enough for a powerful fusion ship may become one of the ship's largest structures. It must also survive impacts, vibration, and years of thermal strain. Fuel brings its own awkward problems. Some fusion reactions need rare isotopes. Others produce more damaging radiation or require conditions that are even harder to create. Collecting, refining, storing, and feeding that fuel would take an industrial system built to standards no present spacecraft approaches. You aren't simply filling a tank before departure. You're supporting a controlled nuclear process for decades, far from any repair yard. That's why fusion deserves respect without receiving a free pass. It may offer the performance a substantial interstellar ship needs. It also asks for mature fusion power, durable materials, immense radiators, precise fuel handling, and decades of reliable operation in one machine. Fusion is the first engine here that sounds less like a desperate trick and more like a possible industry. But the upgrade is larger than the engine. Before such a ship could leave, civilization would need to learn how to build and maintain the whole industry around it. Calling fusion an engine hides most of the machine. The part making thrust needs a reactor, a fuel plant, a magnetic nozzle, heavy shielding, and a cooling system large enough to shape the whole ship. Start with the fuel. Some proposed engines use deuterium, a heavy form of hydrogen found in water. Others add tritium or helium-3. Each choice changes how readily the fuel reacts, how many neutrons it releases, and how hard it is to obtain. Tritium is radioactive and scarce. Helium-3 is scarce too. Even deuterium must be separated, purified, stored, and fed into the reactor with great precision. That takes machinery, energy, and a dependable supply chain long before launch. The reactor must then make that fuel fuse. It has to hold extremely hot plasma away from ordinary walls. Magnetic fields act like invisible rails around a very unruly train. Producing those fields takes powerful magnets, control systems, and electricity. If the plasma slips out of control, you don't simply lose thrust. Heat and radiation can reach equipment that may be impossible to replace. Next comes the exhaust. Hot charged particles must leave in one direction, fast enough to push the ship forward. A magnetic nozzle can bend them without putting a solid nozzle in their path. But now we have another enormous magnetic machine beside the reactor. It must remain aimed and stable while the ship changes speed. Some particles ignore the magnets. Fusion reactions can release neutrons that pass through magnetic fields and strike the ship. Over time, they can weaken metals, damage electronics, and make nearby parts radioactive. Shielding absorbs some of that punishment, but shielding has mass. Use too little, and the ship slowly injures itself. Use too much, and the engine must accelerate its own armor. Then there's the heat. Only part of the reactor's power becomes exhaust. The rest warms the magnets, pumps, shields, power systems, and reactor. A power station on Earth can pass heat into cooling water or the air. In space, there's no river and no breeze. Radiators must release it as infrared light. Those radiators could cover enormous areas. They must stay light, survive impacts, and work for years. Hotter radiators can be smaller, but their pipes and panels must endure higher temperatures. Cooler radiators need more area. Either way, cooling is no longer plumbing hidden behind the engine. It helps decide what the spacecraft looks like. A damaged radiator could also force the reactor to run below full power. So the industrial ladder rises quickly. Build a working fusion reactor. Make it compact, light, repairable, and reliable for decades. Produce fuel at scale. Build magnets that endure constant stress. Develop materials that survive neutron damage. Add shielding without burying the performance under mass. Then build radiators that can shed heat through years between stars. The glowing reactor is only the center. Around it sits a fuel works, power station, cooling plant, and a maintenance yard, all leaving Earth together. That sounds like a strong case against fusion. Yet the same list also explains why fusion remains in the lead. The demands are enormous, but they belong to engineering we can describe. We know what each part must do. We can test magnets, fuels, radiators, shields, and reactor materials one problem at a time. And the reward could be extraordinary. Fusion fuel stores far more energy per pound than chemical fuel. A fusion engine could release that energy as a fast stream of charged particles, push those particles backward, and the ship moves forward. The faster the exhaust leaves, the less fuel the ship needs for a given change in speed. That becomes precious when the payload is large. A crewed interstellar craft may carry living space, food, tools, spare parts, shielding, and machines for making new parts. It can't behave like a tiny probe with a brief working life. It must carry a small world, and fusion may offer enough performance to move that world without making fuel almost the entire ship. But May carries a great deal of uncertainty. No fusion reactor on Earth has yet become a compact, long-lived spacecraft engine. Today's experiments are built in large facilities. They depend on heavy equipment, steady maintenance, and power supplied from outside. An interstellar engine would have to start itself, control itself, survive faults, and keep working far beyond any repair shop. Fuel adds another condition. Some fusion reactions are easier to begin, but they release many neutrons. Neutrons don't respond to magnetic fields. They fly into the engine structure, damage materials, and turn some parts radioactive. Reactions that produce fewer neutrons look attractive, but they usually demand higher temperatures or harder confinement. The cleaner option can become the more difficult reactor. Then there's thrust. A design can look wonderful on a chart because its exhaust is extremely fast. Yet, if it releases only a small amount of that exhaust each second, acceleration stays low. The ship might be efficient and still take years to reach cruising speed. More thrust usually means more reactor power, more waste heat, and more mass devoted to controlling both. So fusion isn't one engine waiting to be assembled. It's a family of possible engines, each trading fuel, temperature, thrust, shielding, and cooling against the others. The winning design may depend less on a single physics result than on an entire industrial base, able to manufacture reliable parts at a scale no space program has attempted. Still, fusion keeps its measured lead. Its physics is known well enough to calculate serious interstellar missions, and its performance could suit ships too massive for weaker engines. What it doesn't offer is certainty. Fusion leads because it gives the strongest combination of speed and physical credibility. It remains conditional because the engine is only one part of the machine, and humanity hasn't yet built the industry that must travel with it. Antimatter looks like the fuel you choose after getting tired of compromises. Matter meets antimatter, both vanish, and their mass becomes energy. On paper, nothing else in the propulsion cabinet comes close. A small amount carries an absurd amount of energy. 1 gram of antimatter meeting 1 gram of matter would release about 43 kilotons of TNT equivalent. That's in the range of a nuclear weapon from something that weighs less than a paperclip. Fusion converts only a small fraction of its fuel mass into usable energy. Antimatter can convert all the reacting mass. You can see why engineers keep returning to it. A ship might use antiprotons to heat propellant, trigger fusion reactions, or produce a beam of fast particles. In the most ambitious designs, the fuel tank stops being the main weight problem. The equations begin offering speeds that make nearby stars feel less unreasonable. Then, someone has to obtain the fuel. Antimatter does appear in nature. Cosmic rays make tiny amounts when they strike other particles. Particle accelerators can also create it. But an accelerator doesn't mine antimatter from a hidden deposit. It spends energy to produce particles, then loses most of them before they can be collected. Humanity's total production is measured in quantities far below what a starship would need. Even if production rose by many orders of magnitude, the fuel couldn't touch an ordinary tank. An antiproton meeting the wall would destroy itself and a matching particle in that wall. So the container must use electric and magnetic fields to hold the fuel away from matter. Those fields need power. The equipment has mass. A fault lasting a fraction of a second could release energy exactly where the ship least wants it. Storage also becomes harder as the supply grows. Holding a few particles for an experiment is one problem. Holding mission-scale fuel through launch vibration, years of flight, power interruptions and maintenance is another. You aren't carrying a passive liquid. You're carrying something that must be actively prevented from touching its container. The engine adds another difficulty. Annihilation doesn't produce a tidy stream of energy that politely leaves through a nozzle. Depending on the reaction, it can produce gamma rays and short-lived particles. Some energy escapes in forms that are difficult to direct. Some strikes the spacecraft. That means shielding, heat removal, and radiation damage return to the mass budget. And the supply chain would be strange even by Starship standards. Production plants would need enormous power. Collection would need extraordinary efficiency. Storage units would have to move without losing confinement. Every transfer becomes a controlled encounter between a valuable fuel and the ordinary matter surrounding it. None of this makes antimatter impossible under a known law of physics. That's part of its pull. The energy is real. The reactions are real. Laboratory containment is real. But the distance between a laboratory achievement and a fueled starship is enormous. So antimatter remains the perfect fuel in the place where perfection is cheapest, the energy equation. It removes one limit so completely that, briefly, you can almost overlook all the others. A tank of ordinary fuel can sit on a launch pad and do almost nothing. Antimatter never gets that luxury. From the moment you make it, the fuel arrives with a list of errands that cannot be postponed. First, you have to produce it. Particle accelerators can create antiparticles by slamming ordinary particles together at high speed. Most of the input energy goes somewhere else. It becomes heat, radiation, and particles you cannot use. Only a tiny share ends up as antimatter you can capture. The amounts made so far are extremely small. Not small like a drop of medicine, small on the scale of individual particles gathered through years of experiments. A starship would need a supply measured for propulsion, not for a laboratory detector. That gap is hard to overstate. Then comes storage. You cannot pour antimatter into a metal bottle. The bottle is made of matter. Contact would destroy some of both and release energy at once. Charged antiparticles can be held away from the walls with electric and magnetic fields, rather like keeping a marble from touching a bowl without letting the marble rest anywhere. That works in carefully controlled traps. A spacecraft needs something harsher. Its trap must survive vibration, acceleration, temperature changes, electrical faults, and impacts from dust. It must keep working through every repair and every maneuver. If the power fails, the fuel doesn't merely become unavailable. It begins meeting the container. A neutral antimatter is even harder to control because electric fields cannot grip it directly. Magnetic traps can hold certain neutral anti-atoms, but only under demanding conditions. The fuel system therefore needs magnets, cooling equipment, power supplies, sensors, backup circuits, and physical separation from the crew. Shielding adds more mass. An antimatter reaction doesn't politely turn all its energy into a smooth push. It can produce fast particles and penetrating radiation. Some of that energy can drive an engine, some heats the vehicle, some has to be absorbed or directed away, which means more structure, more shielding, and larger radiators. Mission planners would also have to decide where the fuel is made. Producing it on Earth means transporting an extraordinarily unforgiving cargo through factories, vehicles, launch systems, and orbital transfers. Producing it in space avoids part of that trip, but moves the giant power plant, accelerator, capture system, and maintenance crew off Earth instead. Even fueling becomes a major operation. Antimatter cannot pass through an ordinary hose. Each transfer has to preserve the trap, while two containment systems connect, exchange particles, and separate again. A loading error involving regular propellant may spill fuel. Here, the spilled fuel reacts with whatever catches it. So the famous energy advantage survives. Gram for gram, antimatter can release far more energy than chemical fuel, fission fuel, or fusion fuel. But a mission doesn't launch an equation. It launches the factory behind the fuel, the equipment around it, and every backup needed to stop a small fault from becoming a violent one. Antimatter may offer the finest fuel by mass, while demanding one of the heaviest systems built around any fuel. That's its constraint. The energy fits inside the ship far more easily than the supply chain does. A warp drive often appears beside rockets in lists of future propulsion. That makes it seem like one more engine waiting for better materials. But the label hides a basic difference. Rockets push matter or radiation backward. Warp concepts ask space-time itself to change shape around a craft. That difference puts warp in another category. You can compare two engines by asking about thrust, fuel mass, waste heat, efficiency, and parts that might fail. Even a wildly difficult engine gives you something physical to place in those columns. A nozzle has a temperature, a reactor has a mass, a fuel tank has a volume. A warp concept doesn't yet give engineers the same kind of object. The best known example is the Alcubierre metric, proposed by physicist Miguel Alcubierre in 1994. It describes a region of curved spacetime that contracts ahead of a craft and expands behind it. Inside that region, the craft would not locally race through space faster than light. The surrounding geometry would do the moving. General relativity allows scientists to write down that geometry. Writing it down doesn't show that nature can build it. The equations call for stress and energy arranged in ways we don't know how to produce. Many versions require negative energy density on scales far beyond the tiny quantum effects measured in laboratories. Other versions change the amount or arrangement, but they don't supply a machine that can create and control the required spacetime. It's a little like ranking a bridge against a shortcut drawn by folding the map. The fold may show how two distant points could touch on paper. It doesn't tell you what holds the land in that shape, how much the supports weigh, or whether the ground can bend at all. Until those answers exist, giving the shortcut a score for construction cost would be make-believe arithmetic. This doesn't make warp research worthless. It gives physicists a sharp way to test what relativity permits, what quantum theory may forbid, and where our theories stop agreeing. Work on negative energy, causality, and curved spacetime can expose gaps in our understanding, even if no spacecraft follows. But a practical propulsion ranking has a narrower job. It compares ideas that can at least be translated into hardware problems. Some may need impossible budgets or materials we can't yet make. Still, their difficulties belong to engineering. Hotter reactors, stronger magnets, larger radiators, better fuel production. Warp hasn't reached that point. There's no agreed device, no demonstrated source for the required energy conditions, and no tested path from the equations to a controllable bubble. Estimates also depend heavily on the chosen geometry, so a lower number in one paper doesn't become a fuel requirement for a future ship. Warp therefore belongs at the edge of the documentary, where the engineering table ends. It marks the border between propulsion concepts we can rank, however harshly, and changes to spacetime that may depend on physics we haven't discovered. Beyond that border, the equations can still guide us. The ranking cannot. So the contest returns to actual ships. They have tanks, engines, radiators, shielding, and people who need to arrive alive. Once those ordinary burdens come back into view, the shortlist changes in the cold between the stars. A drive can look magnificent on a diagram and still carry almost nothing. Thrust and speed aren't enough. What counts is the payload left after the ship carries everything needed to make that speed possible. It's like packing for a long walk. A larger water bottle lets you travel farther. But the bottle and water also add weight. Add food, warm clothes, a tent and a stove, and soon much of your effort goes into moving the supplies that let you keep moving. A starship faces the same irritation, only with radiation shielding and machinery instead of socks. This is why payload fraction becomes such a severe filter. It's the share of the ship's mass that can be devoted to passengers, instruments, habitats, and cargo. Every kilogram assigned to fuel, power systems, cooling equipment, or engine structure is a kilogram unavailable for the mission itself. And the engine can make the problem worse. A powerful system may need a heavy reactor. The reactor may need broad radiators. Those radiators need supports and protection. More mass then calls for more propellant, which may require larger tanks. The additions feed one another until the spacecraft becomes an engine carrying a very small reason for going anywhere. You can see the human consequence in the design choices. A probe may accept tiny payload space because a few instruments can still do remarkable science. A crewed ship can't be squeezed in the same way. People need air, water, food, living space, medical supplies, and protection from radiation. They also need backups, because a failed pump between stars isn't followed by a repair van. Travel time belongs in this filter too. A faster crossing reduces the food and supplies consumed along the way. It may also reduce exposure to radiation and the years spent keeping a closed habitat alive. But if gaining that speed demands vastly more fuel or a much heavier power system, the apparent advantage can disappear inside the launch mass. That brings the ranking down to a less glamorous comparison. How much ship must be built for each kilogram that reaches the destination? How much heat must be removed? How much equipment has to work without rescue? And after all of that is counted, is there enough payload left to justify the voyage? Warp concepts can't answer those questions yet. That's why they sit at the boundary, instead of beside machines that can be weighed and tested. Their role is to show where our practical rankings run out and unknown physics begins. On this side of that line, the contenders are real enough to disappoint us properly. They must carry their own burdens. They must survive their own exhaust, shed their own heat, and deliver something more substantial than an engine. The shortlist now belongs to the ships that can still carry a mission after the accounting is done. A starship carrying people would look less like a giant rocket and more like a small town wrapped around a machine. The engine might set the speed, but almost everything else would keep the passengers alive. Start with air. A crew needs oxygen, carbon dioxide removal, pressure control, filters, fans, pipes, valves, and backup parts. Water has to be stored or recycled. Food needs space, unless some of it grows aboard. Every person also produces heat, moisture, waste, and a steady stream of small maintenance problems. Then there's radiation. Earth protects us with its atmosphere and magnetic field. A ship between stars would leave both behind. Its crew would need shielding against solar storms and cosmic rays. Shielding means mass, and that mass follows the ship for the entire trip. A short mission can pack supplies and accept wear. A voyage lasting decades can't. Pumps fail, seals leak, electronics age, lubricants break down, dust reaches places it shouldn't. The ship needs tools, spare parts, workshops, sensors, and people who can repair systems that may be older than they are. There's no repair shop waiting a few million miles ahead. A generation ship raises the burden again. It must support children, aging adults, medical care, and a stable community. It may need farms, artificial gravity, private rooms, and enough biological diversity to avoid serious genetic problems. Even the boring parts become critical. A broken toilet on Earth is unpleasant. A broken waste system between stars can threaten the whole population. All of this changes how we judge an engine. A propulsion system may look excellent when it pushes a small probe. Add habitat walls, water, shielding, machinery, and spare parts, and the same engine may barely move the finished ship. More mass can demand more fuel. More fuel adds still more mass. The numbers can swell in a rather rude loop. Speed also creates costs beyond fuel. A faster ship needs stronger protection from dust grains. At a large fraction of light speed, even tiny particles strike with enormous energy. The ship may need thick forward shielding, active detection, or both. That protection adds weight exactly where the propulsion system least wants it. And the engine itself joins the habitat problem. Its waste heat must go somewhere. Its radiation and exhaust must stay away from the crew. If it vibrates, fires in pulses, or uses dangerous fuel, the rest of the ship must be built around those habits. So the human payload isn't a box placed behind an engine. It becomes the ship. The engine is one organ inside a moving habitat that must breathe, repair itself, protect its people, and keep doing so without help. Once humans come aboard, the winning design may not be the fastest machine. It may be the one that still works after carrying everything life refuses to leave behind. A generation ship has to carry more than people and an engine. It needs equipment, spare parts, shielding, food production, and living space. All of it must remain a small working world for centuries. That changes the math before the engines even start. A fast probe can be built like a racing bicycle. Every piece earns its place, and failure ends the mission. A crewed ship is closer to an ocean liner that must grow food, make medicine, and rebuild machinery while crossing an ocean with no ports. It needs backups for its backups. That extra mass isn't waste. It's what stops one broken pump from becoming the end of everyone aboard. You can see why some propulsion ideas shine with a light payload. Give them a compact instrument package, and they can reach remarkable speeds. Add a settlement, and their advantage begins to fold. Laser sails are one example. A very thin sail can push a tiny probe without carrying fuel. But a sail large enough to pull a shielded human habitat becomes difficult to build, aim, and keep intact. The laser array back home must pour energy onto it across a growing distance. A grain of dust hitting at high speed can damage the sail. Repairing a membrane spread across many square miles would be an awkward job even in Earth orbit. Doing it between stars, with no supply launch coming, is another kind of problem. Other systems lose less ground as the ship grows heavier. Nuclear pulse propulsion throws explosive pulses behind a massive plate. The ship rides the repeated impacts. The design is violent, politically difficult, and hard on machinery. It also asks the crew to maintain parts that spend years being struck by controlled explosions. Still, its ability to move large loads keeps it on the table. Fusion has a similar appeal. If controlled fusion can be made compact and dependable, it could push a large vehicle without asking the crew to live beside thousands of stored bombs. But no one has built a fusion rocket that can run for the years such a voyage may demand. A promising calculation is one thing. An engine that people can inspect, repair, and restart far from Earth is something else. Beamed propulsion may still help during departure. Antimatter may offer extraordinary energy from very little fuel. Both face severe problems when we ask them to move a town instead of a probe. The power stations, beam control, fuel production, storage, shielding, and braking system all have to survive the same mass test. Even the lightest fuel doesn't make the habitat light. So the shortlist becomes rather blunt. Any system that depends on extreme lightness becomes harder to defend. The survivors are the families that can tolerate weight, nuclear pulse, some form of fusion, perhaps a hybrid that uses outside power early and onboard propulsion later. None is ready, none is gentle. But these are the few that might carry the inconvenient bulk of a human future. A ship carrying people for several generations is less like a vehicle and more like a small town that can never call for a repair crew. Everything the people need must either survive for decades or be made again on board. Start with air. The ship has to remove carbon dioxide, replace lost oxygen, control humidity, and catch chemicals released by plastics, plants, machines, and human bodies. Water must be cleaned and reused. Food must be grown or stored without one bad harvest ending the mission. Waste becomes raw material because there's nowhere else to put it. Then come the parts nobody notices until they fail. Pumps wear down, seals crack, filters clog, bearings lose their smooth surfaces, computers suffer radiation damage, pipes collect deposits. A valve costing a few dollars on Earth can threaten everyone alive if there's no replacement. So the ship needs workshops, tools, spare materials, and people who know how to use them. It may need machines able to make new machines. Those machines need feedstock, power, calibration, and their own replacement parts. You can feel the problem growing. Each answer brings another box onto the ship. People add weight in less obvious ways too. A crew can tolerate tight quarters for a short expedition. Children born during the trip cannot spend an entire life in emergency conditions. They need safe rooms, education, medical care, privacy, exercise, and some way to live together without every disagreement becoming a systems problem. Gravity may add another demand. Years in weightlessness damage bones, muscles, vision, and circulation. A rotating habitat could create artificial gravity, but rotation needs a large structure. Large structures need more material, stronger joints, and careful balance. If the ship carries soil, water, plants, and radiation shielding, the habitat grows heavier again. And shielding isn't optional. Beyond Earth's magnetic protection, energetic particles can pass through tissue and damage cells. Thick layers of water or other material can reduce that exposure. The water is already needed for life, which helps. But every gallon still has mass, and the engine must accelerate it. There's also a social system traveling inside the engineering system. A voyage lasting centuries may begin with trained volunteers and end with descendants who never chose the destination. They must preserve skills, settle disputes, raise children, and decide who controls limited resources. The mission can fail while every engine remains functional. This changes the propulsion problem. The engine is no longer pushing a cabin with a crew inside. It's pushing air recyclers, farms, hospitals, workshops, shielding, archives, living space, and enough backup equipment to survive failures no designer predicted. All of that must keep working between the stars. A fast probe can be a brilliant machine. A generation ship must be a durable civilization. The propulsion system carries both, and the civilization is by far the heavier payload. Once a ship reaches cruising speed, the engines may become the least troublesome part of the voyage. The space ahead looks empty, but empty isn't the same as harmless. Between the stars, a ship passes through thin gas and scattered grains of dust. At ordinary speeds, a dust grain tapping the hull would be unremarkable. At a large fraction of light speed, the ship meets that grain with enormous relative motion. The grain doesn't need an engine. The ship supplies the energy for the collision. It's rather like driving through rain. The rain is falling at its own modest pace, yet the drops strike harder as your car moves faster. Now replace the raindrops with dust, raise the speed beyond anything humans have traveled, and remove the windshield repair shop. Small particles can blast material from the forward shield. Individual atoms can strike hard enough to disturb electronics and damage exposed surfaces. Gas ahead may also become ionized around the ship, producing radiation that has to be managed. The faster the cruise, the greater the burden at the bow. So shielding cannot be treated as a thin protective shell added near the end. It may need deep layers, replaceable sections, magnetic or electric defenses, and sensors that detect larger objects early enough to react. Each defense adds mass. Added mass demands more propulsion energy. More energy often means a larger power system, which adds still more mass. And power has another cost. Machines never turn all their input into thrust. Some energy becomes waste heat, even in very efficient systems. On Earth, air and water can carry heat away. In space, a ship mainly sheds heat as radiation. That requires large radiators. They must stay exposed to cold space, yet exposure makes them vulnerable to the same dust and debris the forward shield is meant to stop. A powerful drive may therefore carry a broad, delicate cooling system beside one of the harshest particle streams the ship will ever encounter. Engineering has a sense of humor, though it isn't always kind. Then comes arrival. A ship moving quickly toward another star cannot simply switch off its engine and coast into orbit. It must lose the speed it spent so much energy gaining. Braking may require another long engine burn, a magnetic sail working against the target star's wind, or some other system prepared years in advance. The ship's mass makes this especially unforgiving. Shielding, radiators, habitats, supplies, and backup machinery all carry kinetic energy. That energy must go somewhere before the travelers can stop. If the braking system falls short, the destination isn't missed by a few miles. The ship passes through the system and continues into interstellar space. Speed shortens the calendar. It also turns dust into ammunition, heat into a design limit, and arrival into a second propulsion problem. The voyage is threatened not only by getting there too slowly, but by reaching the destination too fast to stay. A powerful engine has a problem even when it works perfectly. It can't turn every bit of stored energy into motion. Some energy ends up as heat inside the ship, warming the reactor, magnets, pumps, cables, and anything else carrying power. It's like running a computer under a blanket. The machine may be doing exactly what you asked, but the heat still has to leave. On Earth, a fan moves warm air away. A spacecraft between stars has no surrounding air to carry heat. It can release that energy only as radiation. That means large radiators. They need enough surface area to glow the unwanted heat into space while staying cool enough not to melt. Higher temperatures help radiators shed energy faster, but the machinery and coolant must survive those temperatures. Lower temperatures are easier on the equipment, yet demand even more radiator area. Either way, the cooling system becomes part of the engine. Fusion doesn't escape this cost. Even if a fusion drive converts much of its fuel into thrust, stray radiation and imperfect machinery still heat the ship. Powerful electric engines have the same problem. Their reactors and electrical systems must process enormous amounts of energy, and every small loss becomes heat. Antimatter is harsher still. Its reaction releases energy in forms that are difficult to direct, absorb, or turn into thrust without warming nearby hardware. You can't hide the radiators behind thick armor, because armor blocks the heat they're meant to release. But exposed radiators are fragile. At high cruise speed, tiny grains strike with enough energy to damage surfaces, puncture coolant channels, or tear away sections. So the ship may need several radiator panels, protected plumbing, shutters, repair machines, and spare parts. Cooling creates mass. Protecting the cooling system creates more. The forward shield faces a similar bargain. More speed means more energetic impacts from gas and dust. Stronger shielding adds mass, and accelerating that mass requires more energy. Then the engine handling that extra energy produces more waste heat. The costs begin feeding one another. Arrival collects the bill. A massive ship moving quickly carries a huge amount of kinetic energy, and stopping requires removing it. Engines used for braking must run hard again, which means another period of heat production when the crew may already be relying on worn radiators and damaged shielding. A magnetic sail or other braking device may reduce the fuel demand, but it adds equipment and depends on conditions near the destination. So an engine can't be judged only by how much thrust it makes. It must also survive its own waste heat, protect the surfaces that release that heat, and remain capable of safely slowing everything it pushed across the dark. The hidden cost of speed is a larger ship built to cool, defend, and finally stop itself. A fast ship doesn't cross empty space in peace. At high speed, even thin gas becomes a stream of tiny impacts, and ordinary dust can strike with alarming force. The faster you go, the more protection the front of the ship needs. That protection might include thick layers that absorb impacts, magnetic fields that push charged particles aside, or replaceable shields that can lose material without exposing the ship beneath. None of it is weightless. Every added layer must be accelerated at departure and slowed at arrival. Speed creates its own cargo. The engines add another burden. A powerful drive can't turn all its energy into motion. Some becomes waste heat, much like a phone warming in your hand, except the power involved may be immense. In space, there's no cool air to carry that heat away. The ship must release it as radiation. That means large radiators. They need surface area, plumbing, pumps, and some way to survive years of dust strikes and radiation damage. If the drive runs hotter, the cooling system grows. If the cooling system grows, the engines must push more mass. Then the engines need more power, which can make still more heat. It's an awkward loop, and it follows the ship all the way to its destination. Now comes the part that speed can't bargain with. A ship arriving at another star still has all the motion it gained when it left. If it wants to study a planet, enter orbit, or let people live there, it must get rid of that motion. For a small probe, a fast flyby may be enough. It can race through the system, collect a brief burst of data, and keep going. A settlement ship doesn't have that option. Missing the stop means missing the destination. Braking a massive ship can demand energy on the same scale as accelerating it. Carrying fuel for that second burn adds more mass from the start. Using a magnetic sail may reduce the fuel, but the sail itself must travel with you, deploy correctly, and find enough charged material or stellar wind to push against. A beam from home could help slow a specially designed craft, though aiming practical amounts of power across interstellar distance becomes harder as the target moves farther away. And braking happens late, after the ship has spent years or centuries taking damage. The radiators, shields, control systems, and engines must still work when the hardest maneuver begins. There's no roadside repair crew waiting near the new star. So the best engine on paper may still fail the trip. Thrust and efficiency are only the opening test. The winning system must carry its shielding, shed its heat, survive the crossing, and erase nearly all the speed that made the crossing possible. Only then has the ship truly arrived safely. After all those changes in the ranking, it would be tempting to name one winner. But the answer depends on where we're going, what we're carrying, and when we expect to build it. Over the next 50 years, the strongest candidates will probably stay inside our own solar system. Electric thrusters already move satellites and deep space probes. They provide very little push, but they can keep pushing for months or years. Nuclear thermal engines could give crewed missions a stronger shove, while using less propellant than chemical rockets. Solar sails may carry small craft without carrying fuel at all. None of these turns a trip to another star into an ordinary mission. They solve nearer problems first, moving cargo between planets, reaching the outer solar system faster, and keeping a probe under power where sunlight grows weak. That may sound modest beside interstellar flight, but it's where engines become hardware instead of promises. For tiny probes, the interstellar answer could arrive sooner. A very light sail, driven by a powerful laser beam, might reach a nearby star within a human lifetime. The craft wouldn't need to carry most of its propulsion system. The heavy equipment would remain near Earth, where people could maintain it. That changes what counts as the engine. The probe may be small enough to hold in your hand, while its launch system stretches across a large site. It would need huge power supplies, many linked lasers, precise tracking, and a way to keep the beam on a sail racing away from us. The mission depends on an entire working network back home. So a probe-class winner isn't just a clever spacecraft. It's a spacecraft plus infrastructure that doesn't exist at the needed scale yet. Build that system, and laser sails become serious contenders. Without it, they remain excellent physics attached to an unfinished machine. A generation ship sits in a different category. Its engine must move a habitat, not an instrument. The passengers need air, food, water, medicine, spare parts, and protection for lives that begin and end during the trip. Even a superb fusion engine wouldn't settle whether such a society could remain healthy and stable for centuries. Fusion may become the leading contender for that kind of vessel. Antimatter could offer still greater performance, but neither is ready to carry a city between stars. We can't yet run a power-producing fusion reactor on Earth as an everyday commercial machine, much less one built for a starship. Antimatter is harder still. We make minute amounts at immense cost, and have no practical way to store the quantities a large mission would require. That leaves us with 3 different answers. For the next 50 years, advanced solar system engines are the likely winners because they match missions we can actually prepare. For interstellar probes, beamed sails may win only after we build the power and aiming systems around them. For generation ships, fusion and other high-energy ideas remain conditional on engineering, economics, and a civilization willing to support a project longer than one human life. The physics gives each class a candidate. Readiness gives each one a different clock. So the winners separate into 2 rather different groups. One group can move real spacecraft within the solar system. The other may someday send something tiny across the gap between stars. Sharing the word engine doesn't make those jobs comparable. For missions we could begin preparing within the next few decades, electric propulsion has a strong claim. Ion and Hall-effect thrusters already work in space. They push very gently, but they can keep pushing for months or years while using propellant sparingly. NASA's Dawn spacecraft used ion engines to orbit both Vesta and Ceres. That was a practical demonstration, not a sketch on someone's desk. Nuclear electric systems could supply more power where sunlight grows weak. Nuclear thermal rockets offer a different advantage, stronger thrust for crewed trips, using a reactor to heat propellant instead of burning fuel with it. Neither system turns a spacecraft into an interstellar ship. Both can make the solar system more reachable. A probe crossing to another star faces a stranger verdict. Beamed sails avoid carrying most of their energy source. A powerful laser array stays near home and pushes a very light sail from far away. That gives a tiny probe a chance at a meaningful fraction of light speed. But the sail isn't the whole machine. The machine includes the laser array, its power supply, precise aiming, heat control, and some way to communicate with a probe after decades of travel. Until that surrounding structure exists, the winning vehicle is missing its engine in the same way an electric train is missing its engine when there are no power lines. Then there's the awkward middle, a substantial spacecraft carrying instruments, shielding, repair systems, and perhaps people. Here, nuclear pulse propulsion deserves attention because its basic physics is established. The craft would ride repeated explosions behind a massive shock-absorbing plate. It sounds like a terrible day at a launch site, and from Earth it probably would be. Yet studies such as Project Orion showed why engineers took it seriously. Nuclear explosives contain enormous energy, and a large ship can carry equipment that a gram-scale sail cannot. Established physics doesn't mean acceptable engineering. The ship would endure thousands of violent pulses. Its launch, testing, treaties, fallout risk and stockpile would create problems far beyond propulsion. Building it in space could reduce some dangers while adding a huge construction effort before departure. It's a contender for heavy interstellar craft because the energy source is real, not because anyone is close to approving the machine. Generation ships sit farther out. Fusion may offer a cleaner path if reactors can produce sustained power, survive for generations, and feed an engine efficiently. Those conditions haven't been met. The split verdict is plain. Solar system missions have engines becoming practical now. Tiny interstellar probes have a possible winner that depends on infrastructure we haven't built. Large inhabited ships have serious candidates, but no ready design. Their hardest requirement may be the civilization behind them. So the answer for a human starship is still no. We don't have an engine ready to build for a ship carrying generations of people between stars. We have proposals, early experiments, and some physics that appears sound. None of that adds up to a machine a crew could trust with the lives of their grandchildren. That answer doesn't make the engine research pointless. It tells us where each kind of engine belongs. For the next few decades, the strongest designs stay close to home. Electric thrusters can move cargo with very little fuel. Nuclear systems may shorten difficult trips and supply power far from the sun. Chemical rockets still do the violent work of leaving worlds and changing speed quickly. These are solar system engines. They can improve exploration without pretending the nearest star is just another destination. Small probes change the ranking. A probe weighing a few grams doesn't need air, farms, shielding, or room for people. A powerful laser array might push a light sail to a meaningful fraction of light speed. But the sail is only the traveling part. The engine is spread across an entire system of lasers, power stations, aiming equipment, and launch operations. Build that system, and tiny probes become plausible. Without it, the sail remains a beautiful piece of material waiting for a civilization-sized flashlight. Heavy probes and inhabited ships bring us back to nuclear energy. Fusion has the best balance on paper. Its fuel could carry far more energy than chemical propellant, without some of the worst features of antimatter. Yet controlled fusion on Earth still hasn't become an ordinary power source. Turning it into a compact engine that runs reliably for decades is another task again. Fission fragment engines and nuclear pulse ships may be less elegant, but elegance isn't the test. Their underlying reactions are known. Their trouble lies in materials, heat, mass, radiation, cost, and the uncomfortable business of setting off repeated nuclear explosions behind a vehicle. That last detail tends to make planning meetings memorable. Antimatter sits at the far edge. It offers extraordinary energy per unit of mass. We can make tiny amounts. We cannot produce, store, and handle anything close to the quantities a large starship would need. For now, antimatter is a physical possibility with an industrial gap so wide that the engine almost becomes the smaller problem. These families remain contenders only under a much larger civilization. Such a civilization would need immense energy supplies, permanent construction in space, closed ecosystems, reliable medicine, and institutions that can protect one project across many human lifetimes. The starship would be the final product of that system, not the invention that creates it. So there's no build-ready generation ship engine in the present source base. There are good engines for our own solar system, a possible route for tiny probes, and several conditional ideas for very large craft. Human interstellar travel still depends less on finding one brilliant engine than on becoming the kind of civilization that could build, launch, and sustain it. Reaching another star has two very different meanings. We can send a machine across the gap with technology that already has recognizable parts. We can't yet send people with the same confidence. Those are separate engineering problems, even if both ships point toward the same light. For a small probe, the best answer may be brutally simple. Make it light, push it hard. Accept that it carries little, cannot repair itself, and may never slow down. A brief pass through another star system could still return extraordinary measurements. The probe only has to stay alive long enough to observe, record, and send its findings home. A larger robotic mission changes the calculation. More instruments need more power. More power adds mass. Braking adds still more. The ship must work after years in deep space, where nobody can replace a failed part. It may need to make decisions before Earth can answer. Suddenly, the engine is sharing the mission with shielding, navigation, communication, and machines built to endure. A human ship changes it again. Now the payload breathes. It needs water, food, warmth, medical care, and protection from radiation. It needs room for mistakes. It may need artificial gravity or some other way to limit the harm caused by years without weight. Every added safeguard makes the ship heavier. Every extra year gives small failures more time to become large ones. That's why there's no single fastest route to the stars. There's only a best route for a particular job. Ask 5 things. What must the ship carry? How soon must it arrive? Does it need to slow down? How much energy can we supply? And what condition must reach the other end? A design can look wonderful until one of those questions changes. Remove braking, and extreme speed becomes easier. Add people, and endurance may become more important than speed. The first craft we send may be tiny and nearly impossible to see. It may cross the solar system faster than any object we've built, then spend decades traveling through almost empty space. Its report could be only a thin stream of data reaching antennas on Earth. No footprints, no colony, just measurements from a place that once existed only as a point in a telescope. That would still count. Human travel belongs to a different scale of effort. It may demand new engines, better materials, closed life support systems, and energy projects larger than anything now devoted to spaceflight. It may also demand patience across generations of engineers who know they won't be aboard the finished ship. The machine would be built by a civilization able to hold one purpose for longer than a career, an election, or perhaps a lifetime. So the distance between stars isn't merely a number of miles or kilometers. It's a test of what kind of mission we mean, what risks we accept, and how long we can keep building toward one destination. A probe may reach another star first. People may follow much later, if they follow at all. Both outcomes can be true without diminishing either one. For now, the stars remain far away, but they're no longer beyond thought. We can measure the gap, test the engines, count the costs, and choose the first small thing worth sending across it. That's how an interstellar age would begin, not with a sudden leap, but with a civilization learning to make one promise last long enough to arrive.